At the microscopic level, quantum systems evolve smoothly. The equations show probability waves flowing and mixing without interruption. But the moment we measure them, that smooth flow stops. The system instantly snaps into a single form. Standard physics textbooks explain this sudden physical collapse with one word. They state that the wavefunction collapses because it interacted with an observer. Yet, if you look through those same textbooks, or ask founders like Irving Schrödinger, you will not find a physical definition of what an observer actually is. Physics built its most successful theory around a pronoun without an antecedent. Nature abhors a vacuum, and philosophy rushed in to fill this one. We have spent nearly a century debating whether human consciousness forces reality to choose a state, or if the universe constantly splinters into infinite parallel timelines every time a particle is measured. The observer resonance theory offers a mechanical explanation. To see exactly how it works, we are going to take a single quantum measurement, slow it down to a microsecond crawl, and watch the precise sequence of potential becoming reality. To understand the physical universe, we must first strip away human-centric philosophy and define the actual mechanical anatomy of an observation. A superposition is often described as a particle physically existing in multiple places at once. This is a misunderstanding of the mathematics. Before a measurement, the wave function exists as an unresolved potential, a field of mathematically possible outcomes that lacks a physical reference point. For our autopsy, we will use a basic physical subject, a simple photodetector. It has no brain, no mind, and no consciousness. This diagram shows the operational definition of an observer. It is any bounded system that acts as a local entropy sink. It takes in disordered environmental chaos, pulling random thermal noise across its boundary, and reorganizes those inputs into internal structural coherence. The physical interaction begins the exact microsecond the boundary of this thermodynamic system makes contact with the unresolved quantum potential. Observation acts as a physical engine. It processes entropy and forces an interaction with the surrounding quantum field. This landscape visualizes textbook collapse. In reality, it's a deterministic resonance lock. The detector's oscillators synchronize with the quantum system, sliding directly into a stable well. The specific lock weighs quantum overlap against thermodynamic cost and geometric impedance. The outcome is fixed by physics. If it's a deterministic equation, why does quantum mechanics look like random chance? This pullback reveals the entropy shadow, dictating the Born rule. Randomness is an illusion of thermodynamic limitations. No finite observer can see the environmental static and hidden variables driving the lock. The universe does not play dice. Probability is simply the shadow cast by our incomplete view of a highly complex clockwork process. The final step of our autopsy concludes when the resonance lock finishes. A stable physical record is formed inside the boundary of the detector. This leaves us with an observer relative reality. Particles do not possess a fixed history or a definite state until they physically interact with an observer's boundary. This dismantles the concept of a classical objective universe, the assumption that things exist in a definite state whether we look at them or not. It breaks a principle physics spent centuries protecting. Reality is an ongoing, active process of bounded systems resisting total thermal equilibrium, carving order out of chaos. Human consciousness performs a physical role. By maintaining our physical boundaries and processing entropy, we serve as the vital engines that continuously force the unresolved potential of the cosmos into a definite, crystallized reality.